We'll have a graph G. We'll define graph G to be a pair of elements, something we'll call vertices or dots, and a subset of the elements from the product of Cartesian product of V by itself. That is a subset from the pairs of elements of V. All right, so what do we mean by this? A middle school student asked you what a graph was, what would you tell them?
So it's it could be a single node or a bunch of nodes, and then they can be connected by edges, the connections in between them.
Yes, that is exactly right. So the definition of a graph that you gave was perfect. We'll give a strict definition in a second. I'm checking the attendance. Do people see the attendance right now? It should be updated. Example of a graph. So we'll have, we'll distinguish between directed and undirected graphs. And then what's to come, please take your mind back to the first part of this course. If you remember, if you don't remember, it's fine. When you talked about selecting elements from a bag of elements, you had a bag of n elements, you reached in and without replacement selected k elements at a time, or you selected k elements with replacement. Let's see the connection to combinatorics actually. So you have a set V of n elements. Let's take 4 elements, A, B, C, and D. Okay. Now, let's think of a general case where you get to select 2 elements at a time where the order of the elements matters. That means that AB and BA are different elements, are different. Okay, so here's my A, B, C, and D, and I'm going to draw them as dots. So here where they're going to be different, A, B, C, D, my dots. So if I select AB, just to indicate that A came before B, I'm going to draw an arrow here. It's just a visual representation of this pair of elements. And if I happen to draw a B, return that B back to the, let's say, bag, and then draw A the second time, that sequence of drawn elements, BA now this time, is different from AB, because the first time I drew A first and then B. Now I'm drawing B first and then A. I'm going to denote this by marking an edge from B to A. This is nothing but a visual representation of a draw from a bag of n elements, where the order of the elements matters. Now, if I'm also doing a draw from the bag of these 4 elements with replacement, it is quite possible that I draw C on the first draw and then C on the second draw. So if that's the case, then I'm going to draw a little loop around C that represents the pairing of C with itself, and so on. So if I draw a CD, I'm going to have an edge like that. Okay. If I draw a DA, I'm going to have an edge like that, and so on. So what I've drawn here is my set of edges is a subset of all possible pairs of elements from V. That is, E is a subset from this Cartesian product. So is it clear to everyone what this product is? Okay. So in this particular, which subset? I can enumerate all the, so I have a finite set. I can enumerate all possible elements here. So I have AB, I have BA, I have DA, and I have CC. Okay. So these are all possible elements here. So you can draw this Cartesian product if you'd like. Here's your A, B, C, D. Okay, so if you'd like to represent it this way, that's fine. Okay, so how many elements do I have? What's the, if I'm not allowed to draw more than, if I'm not allowed to do AB and AB again, that is, I'm not allowed to draw 2 edges here, like AB and AB, suppose that's not allowed. If I draw an AB once, that's an AB. What's the most number of edges that I can have? That is, I'm asking, what's the cardinality of this? That will be, that is how many elements, how many pairs of elements do I have, is essentially the question. How many? So here, in this example, the number of elements in E was 4. These are these 4 edges. This one, this one, this one, and this one. Actually 5, right? A, B, C. Well, what am I missing? D, A, C, D I'm missing. So I have an edge C, D as well. So I have 5 elements. The number of elements in E. So which 5 elements did I pick? These 5 elements. AB I picked. BA I also picked. DA I also picked. CC I picked. And I picked CD. So currently these guys, these guys, this is a subset of V. Where's V squared? Where's V times V? It's all these dots. I have n squared dots. Which subset did I pick? Well, whatever's marked with edges here. There's no difference. So a graph, just drawing a graph like this, it's just recasting this combinatorial problem of drawing some elements from a bag. It's nothing, it's not much more than that. Okay, but we find it convenient to draw these things on a piece of paper, just with these edges. Now, this object here is called a directed graph, a digraph, directed graph, graph G. You can also have undirected graphs. An undirected graph where you draw is where you draw those elements from a bag without replacement. The order now does not matter. So what you do is you reach into the bag and draw 2 elements at a time. If you draw A, B, there's no notion of order. Did A come first before B, or did B come first before A? That doesn't matter. You reach in, you draw 2 elements. Obviously, you cannot draw the same element while you're drawing 2 of them. So there's no CC or there's no AA or anything like that that can be drawn. You draw AB, and that's the AB that you draw. Now, the way you put this kind of graph on a piece of paper is as follows. You go AB, and either you draw that pair, in which case you draw an edge between A and B, or you don't draw a BC pair, for example, then there is no edge between them. Okay, so this is like one possible graph that you can have. So here, what's, again, E is still a subset of this, but now it's a different kind of relation. Now, what's inside this element? How many edges do I have? Now, when I draw AB, that's it. That's BA. That's AB or BA, doesn't matter. The order does not matter. And you know what I'll be asking next? What's the maximum, how many different ways I have of drawing 2 elements at a time from a set of n elements? I don't know if you denoted this by k elements from n like this, or you have this notation, which is the notation I use, because it's more common in probability. Might as well use this one in combinatorics too. But I don't know, whichever, you know what I'll be asking. How many different ways are there of drawing these edges between pairs of elements? So in this case, I didn't draw all of them. I could have drawn AC and I could have drawn BC, but I don't have those. I just have AB, BD. I have CD. And I also have AD. I just drew 4 edges here. Okay. What's the maximum number of edges I can have? Let's say if the number of elements in V is 4, just this example that we have on this slide now, and then we'll generalize in a second. So what's the max number of edges that I can have? And if you're thinking in terms of combinatorics, if you are, if you're not, that's fine too. You can just reason through this just by looking at the pictures. But I guess the question then, it's clear to you, the question that I'm asking is how many different ways are there to draw 2 elements at a time from a bag of n elements? In this case, n is 4. From a bag of 4 elements, how many different distinct pairs can I draw?
It's just 8.
Why is it 8? Which 8?
Oh wait, no. It's 6.
Okay, it's 6.
Yeah.
It's 6. And which 6 are these? The ones that are drawn and 2 more of these. This accounts for all possible edges. Now, a simple graph is one, an undirected simple graph is one where you have at most one edge between every pair of distinct nodes or vertices. So you either have an edge, if you have an edge, just one edge, that's it, or you don't have an edge. Okay. If you have every edge possible, let's go, do we have another scratch paper? Let's go with 5. So let's take G. Again, every graph is a bunch of vertices and a bunch of edges, which is a subset from the pairs of V's. So let V be 5. 1, 2, 3, 4, 5. 5 elements. A, B, C, D, E. So what's the maximum number of edges that I can have? And soon I will be asking you the next question. Now, let V be n. What is max E for a simple undirected graph? Simple undirected graph. Okay, but that's to come in a minute. For now, let's just work with the 5. How many edges do I have?
Maybe 10. I don't know. I
Yeah.
don't.
So that's correct. Why did you say 10? That is correct. That is correct.
I kind of did it, or well, first I did it in my head, and I was thinking, is there a pattern? And I think is it just I don't know, is it just double whatever the amount of dots you have?
No.
Well,
That's incorrect.
yeah, I just did it in my head, so I think.
Okay, so it's one thing to account for. If you have 6, then it's not going to be 12. It's going to be much more than that. Well, it wasn't double when we had 4, right? When we had 4 vertices, the number of edges we have was 6. It's not double 4. But you're drawing 2. How many different ways are there of drawing 2 elements at a time? If you know the answer, just let's keep that aside. Let's just directly count the number of possible edges. Let's start from A. Now, if I have all possible edges, that means every pair of vertices is connected. A is connected to 4 remaining vertices. So I have a total of 5 vertices. So I have 4 of these vertices that are emanating from A. Now I'm going to go around clockwise, and I'm going to add edges. So that I've accounted for 4 edges. Now I get to B. B is connected to every other vertex. But one of these vertices I've already accounted for from A. So the new vertices that I have is to C, to D, and to E. So I have 3 new edges that I have. Now I'm getting to C, and I want to connect C to every other vertex, but 2 of those connections have already been made before. So now I'm connecting C to D and E. So I have 2 new connections. Okay, so let's draw those, this one and this one. So I continue, I go to D. D must be connected to every other vertex, but 3 of those 4 I've already drawn. So the 4th one, so there's only 1 new one that I'm adding to it. And finally, I get to the last vertex, and it's connected to every one of the remaining ones, but all the vertices, all the edges are now drawn. What is the sum of the first n minus 1? So V is n. So this is n minus 1 plus n minus 2 plus blah, 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 plus 2 plus 1. What is the sum of the first n minus 1 elements? You proved this by induction. What was the sum?
N minus 1 factorial?
No, so factorial is the product of those terms.
Yeah, never mind.
Okay, so I'm summing up those terms. I just want to know what the sum is. 1 plus 2 plus 3 plus 4 plus blah, 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 plus n minus 1. It's going to be this. You proved this by induction already. So for example, here, 4 plus 3 plus 2 plus 1, that's going to be 10, otherwise known as 5 times 4 divided by 2. Okay, and if you count the number of edges here, the number of edges, it is 2. And this works for when if n were 6. So for example, in 6, let's account for every edge. So here, all the edges. What's going to be the answer? How many edges?
21? Or wait, sorry, oh, 5 plus 4, sorry, yeah. 15.
Right.
Yeah, not 6. Yeah, sorry.
Yeah, so 15. Okay. Now, okay, so now this is because you knew that the sum of the first n minus 1 elements is going to be this number, n times n minus 1 over 2. Okay. Now, what is from a previous class or from high school, whichever it was, you have a bag of n elements. We started this class by claiming that drawing these edges in a simple graph, in a simple undirected graph, is like picking 2 elements at a time from a bag of n elements. N is the number of vertices, and because edges are drawn between pairs and picking up pairs, if I picked up this pair, I drew an edge. Picked up that pair, I drew an edge, and so on. So how many different ways of picking out pairs are there? How did you denote this? Like n choose k, did you denote like this, n choose k?
Yeah, it would. Well, I was going to say like it's n choose 2, and so it's n factorial over 2 factorial times n minus 2 factorial.
That's
That
exactly right.
simplifies, yeah.
And that simplifies to what?
N times n minus 1 over 2.
Exactly. So this, if you wanted to think about it that way, you would have gotten exactly the same answer, which is exactly the same as that. Right? So the point that we're trying to make is that if you draw in a simple undirected graph, every edge that you can possibly draw, then the number of those edges will be n choose 2, n times n minus 1 over 2. So in a graph, there's a special notation for a graph like this. A graph on n vertices where you have every simple graph, where you have every possible edge. You have exactly one edge between every pair of vertices. Such graphs are called complete graphs on n vertices. Complete graph on n vertices. And is denoted by k. And k does not stand for some German word for complete, which it does, but that's not why k is there. It's named after Kuratowski, who was one of the people who worked on graphs in the 20th century. So it stands for K, complete graph on n vertices. It's a standard notation in graph theory. Okay, so we'll see other kinds of graphs. We'll have this nomenclature of graphs. We'll talk about complete graphs on n vertices. We'll talk about bipartite graphs. We'll talk about cycles. We'll talk about wheels. We'll talk about Q graphs, and so on and so forth. But yeah, we'll classify them later. For now, let's move on with a few more definitions. And then let's get to interesting stuff, but we'll get the definitions out of the way first. First thing I want to define is the neighborhood of a vertex and the degree of a vertex. So I'll return to this slide. Here are the definitions. By the way, we're going to skip these slides with modeling. Graphs are used to model all these situations. That's a sort of a very light reading of the textbook from chapter 10.1. We're skipping completely that chapter because you'll see applications of graphs all the time, and there's no need to devote a complete lecture to the applications that can be of graphs. As the applications come up in our discussion, we'll talk about them as they come up, and we'll see many, even in this class. But you always see them throughout. But to spend a couple of minutes, let me tell you, here's one example where a graph models some kind of situation. I don't know what it is. It could be some setup for an airline. Let's say this is American Airlines in the time frame from 9 a.m. to 2 p.m. you have all these flights available. There's one flight from LA to Denver. There is no flight from LA to Detroit, but there are all these flights. And if there's a flight within that time frame, I'm going to draw a line between these two cities. The cities represent the nodes, and the flights represent the edges. It models something. Maybe the airline is using this graph to solve some kind of problem. We'll later see how graphs can be used to solve specific problems. There are other examples with computer networks. Again, we're not spending time on this kind of stuff because it's pretty intuitive, pretty obvious. You should just look at chapter 10.1. If you have any questions, by all means ask me, but it's very, very straightforward and intuitive. Okay, but let's talk about a few terms that we'll be using throughout. So suppose you have a graph G. You say the two vertices are adjacent if there is an edge between them. So U and V are adjacent if there is an edge between them. So for example, in this graph, every pair of vertices are adjacent. So A is adjacent to B. Why? Because there's an edge between them. In fact, this is true for every pair in this graph. If you had a graph like this, okay, A and B would be adjacent, and C and D would not be adjacent. In fact, D is not adjacent to anything. And you can have this, we'll call later this one, this graph here, this G and 4 vertices will turn out to be a disconnected graph. Again, a very intuitive notion, what a disconnected graph is. Okay, we'll give a strict definition later when we will have a notion of a path, but you look at the graph and yes, it's disconnected. This is a disconnected graph.
I'm out of breath, Brian. I'm really...
What is it? Okay, so that's that. Now, a neighborhood of a vertex is the set of all the vertices that it's adjacent to. So for example, in a graph like this, suppose you have a graph. Okay, so this is a graph. This is A, B, C, D, F, E, G, H. What's the neighborhood of A? It's simply a set of vertices to which it is adjacent. So A is adjacent to B, to C, and to D. That's the neighborhood of A. The number of vertices in the neighborhood of A, that is the cardinality of that set, the number of elements in that set, is called a degree of a vertex. Okay, so what's the degree of E in this graph? What's the degree of E?
3.
3, because it's adjacent to 3 vertices. So these guys, the number of vertices that it's adjacent is the number of edges that are incident to it. So the number of the edges emanating from E, the number of those edges is the degree of E. G, the degree of G is 1, and such a vertex is called a pendant vertex if its degree is 1. And in this graph, the degree of D is 0. It is called an isolated vertex. Okay, so that's about it. There's one more thing we should say about the neighborhood of a set of vertices. A neighborhood, suppose I want to look at the neighborhood of a set of vertices like A, D, and E. Suppose my set A is a bunch of vertices. In this case, A, D, and E. What's the neighborhood of this set A? It is simply the union of the vertex A with the neighborhood of vertex D, and the union of that with the neighborhood of vertex E. So let's see what those are. What's the neighborhood of vertex A? We just found it here. It's B, C, and D. What's the union of this? What's the neighborhood of vertex D? What's the
It's A and F.
A and F? And what's the neighborhood of vertex E?
C, G, H.
C, G, and H. So what's the answer then? What's the neighborhood of this set A? Does that make sense? I've excluded A, D, and E from consideration here. So the red set, A, D, and E, so these guys, what's their neighborhood? The neighborhood is C, B, F, and H, and I forgot G here. Should be G is here, so I didn't include it. So let's include it now, G. So G is going to be in the neighborhood. Well, in this case, it turns out it's the whole graph. Does that make sense? This is, by the way, called a vertex cover, but that's a separate issue. Any questions about the definition so that we can get this out of the way? And it looks like we have. These are all the definitions that we need. And now we're going to move on to something more interesting. Okay, so you're on a job fair, or let's say at a party or something. And let's say you have like 5 people that go into the party. Okay, so you have Alice, Bob, Carol, Doug, and Elizabeth. Okay, so all these people walk in, and some people shake hands. Okay, some people don't shake hands. So suppose A shook hands with C, and E. B didn't shake hands with anybody. C shook hands with A. Oh, maybe B shook hands with C. Okay, and C shook hands with E as well, and maybe D shook hands with, I don't know, maybe with A. Okay, let's do it that way. Okay, these are all the handshakes. So these people shook hands with one another. Some people didn't shake. So for example, A and B did not shake hands, whatever. D and E didn't, C and D didn't. So what I imagine for a second, that there's a host at this party. Let's suppose I'm the host, and I walk up to every person. I walk up to A and ask A, how many people did you shake hands with? And A reports that he shook hands with Alice. She shook hands with Carol, Doug, and Elizabeth. So 1, 2, 3. So how many handshakes did she do? 3. Bob, I just shook hands with Carol. That's it. That's it for Bob. Just 1. Carol, 3. Doug, 1 again. Elizabeth, just 2 people. So I collect this data from these people, the attendees, and I sum them up. So I write down the total, and the total is going to be an even number. That's my claim. So let's see here. 3 plus 1 plus 3 plus 1 plus 2, that's going to be 10. So I have the total number of handshakes reported. So number of handshakes reported is even. So what I'd like you to help me prove is that this holds in general. See why it should be true that this total number here that the host registers when he asks people for their number, the number of people they shook hands with, it's going to be even. By the way, can I ask you one more thing before you answer this? Like, what is this 3 in terms of the definitions that we gave for A? The number of times A extended his hand to perform a handshake.
The degree.
A degree. That's the degree of A. That's the degree of A. So these are degrees of those nodes or vertices, degrees of C. So the sum of the degrees here is going to be even. Why is that the case?
Because 2 people take part in each handshake.
Okay, and good point. And
Because if you increase the degree of one vertex, you're increasing the degree of another. So you add 2 to the total every time.
oh, that's a good point. That's what you're suggesting now is those ideas will come up in constructive proofs. That answer needs further clarification, but it's a good one. But let's argue differently. So when I went around, right, and I asked, let's say I let's start at A and go around like counterclockwise. And every time I report a handshake, I'm going to mark that handshake with like a little line here. or whatever you call it, like tick. So A reported 3 ticks. By the way, what's a handshake? A handshake, an edge represents one handshake in this graph, right? Everybody agree? One handshake is an edge. So A, when I'm done with A, the degree of A being 3, A ticked off like 3 of those edges of the entire graph, of all the handshakes. He ticked off like 3 of them. When I went to B, he ticked off 1. Now notice what happens when I get to C. C also ticks off 3, but C's ticks made this edge between B and C being marked. This led to that edge being marked twice. Same thing happened with this edge between A and C. There is no way for me to mark these 2 edges any more times, right? Because as you said, each edge, each handshake corresponds to a handshake between 2 people. So when those persons are done reporting their handshakes, the edge, the handshake between them, is accounted for exactly twice. And because there are no other persons involved in that handshake, no one else will report that same edge. So there's no way for me to have like 3 tick marks or 17 tick marks on any of these edges. And there's no way for me to have just 1 tick mark or no tick mark, as long as everyone reports the handshake, which it's assumed that they do. So as I go around, notice that each of these handshakes is marked exactly twice. So the sum of the degrees of these guys has got to be twice the number of handshakes. Let's denote that number by M. Let M be the number of handshakes. Handshakes, which is the number of edges in this graph. So twice the number of edges in this graph happens to be, is the sum of degrees of all the vertices. Does that make sense to people? Well, also twice the number of edges in any graph will be the sum of the degrees of all the vertices. That happens always. It is always true. It's true in more general cases, although we're talking here about undirected graphs. And in undirected graphs, even if it has these like multiple edges, it's still true.
So can we say like this? For example, A and C handshaking with each other.
Mm-hmm.
With that way, C and A doesn't have to handshake with each other again. They already handshake, right? So
Yeah.
actual counting handshake is a 5.
Is a
Is
5?
that correct? No, actual handshake is 5 as a person. Imagine there are people, and actual handshaking is a 5, but A and C counting as 2 because when they're shaking each other, it's counting for an A and also for C2, right?
Okay, so let me understand. I'm not quite understanding. So when you ask for a handshake, so first 5, did you mean that you have like 5 handshakes total? Or what do you mean by 5? Maybe I misunderstood.
Yeah. When people hold their hands together, let me say like this, there's 5 times 2 hands holding each other's. Well, yeah, 10. Normally 10, because we counting one person, A and C, as a 2. Because normally when they handshake each other, it's counting for an A and C. Did I explain myself? So what I'm trying to say, it's a little bit like, I just imagine the people standing in front of them as a pair, for example, A and C, standing them face to face and handshaking. We're counting that handshaking as a 2 because it's counting for an A and C.
Yes.
But actual handshaking is 1.
Yes.
That's what I am trying to say.
Yes, that's what we said with this argument, didn't we? Roughly what we said.
Yeah.
Right. So yes, that is true. Okay, so I was misunderstanding you then. So yes, each handshake is accounted for twice, once from A and once from C. And I've taken accounts from everybody, and each handshake was reported exactly twice. So that means that twice the number of handshakes is the sum of all reports. That is the sum of all degrees, the sum of all degrees of whatever vertices I have in this graph, all the vertices, whatever the vertices are in G. So for the graph G is all the vertices and all the edges. Okay, so for this G, this is true. This is called the handshake lemma. So let's box this. This is called the handshake lemma. Handshake theorem or handshake lemma, or the fundamental theorem of graph theory, just as algebra and arithmetic have their fundamental theorems. There's a fundamental theorem of calculus. There's one fundamental theorem of algebra. There's fundamental theorem of number theory. And there is fundamental theorem of graph theory. And this is, or sometimes called the zeroth theorem of graph theory. That's the handshake lemma. This identity here always holds. Now let's do something interesting with this identity here. Okay, I'll ask you this in a second. This will be very straightforward. Let's start here. So you have a tournament where people play games. Okay, it could be like a boxing tournament or an, like, I don't know, a chess tournament or an MMA fights. But the idea is that two persons are involved in some kind of competition. Okay, so it's like let's stick with tennis, singles tennis tournament. The structure of the tournament itself can be very complicated, but the point is, like, each time a game happens, two persons meet. Okay. Here's what we'd like to prove: that the number of people who have played an odd number of games is even. It may take a minute to parse this, but let's see what's happening. So you have some number of people participating in this tournament, right? Some people, each person plays some number of games, right? And I suppose Alice played 5 games, Bob played 22 games, and Carol played 7 games. So Alice and Carol, who played 5 and 7 games, two of those people, each played an odd number of games, right? And what we're trying to prove here is that the number of people, like Alice and Carol, who played an odd number of games must always be even. So I cannot have, like in a tournament of like 17 people, I cannot have just Alice, Carol, and Zelda play an odd number of games each. For example, Alice playing 5 games, Carol playing 7 games, and Zelda playing 19 games, and other people playing even number of games each. Like this guy playing 22, that guy playing 2166, that guy playing 0, the other guy playing 4, and so on and so forth.
I have a question.
Yes.
Would the number, so it's 127 people. Is that important? Do they have to be an odd amount of people for this theorem to hold true?
Okay, so it turns out, no, it doesn't have to.
Okay, I was gonna.
But okay, so it can be 17, could be 18 people. In general, so we'll generalize this. We'll have n people, but let's stick with some number just to have a concrete number here. Okay, but the point, but is it clear what we're trying to prove?
Yeah, it's clear.
Yeah, that the number of people, those people who played odd number of games, an odd number of games, like Alice, Carol, and Zelda, they played an odd number of games each person. Their number, it cannot be that it's Alice, Carol, and Zelda. There must be somebody else at least, so that their total number of those people who played an odd number of games each, that number, their total number must be even. Make sense to everybody? Convincingly?
Can you assume the opposite?
Oh, okay. So let's try that one.
Can you assume the opposite and disprove?
So can we try that one?
Maybe.
Okay. So we have 127 people, right?
Okay.
And let me take those people who have played an odd number of games. People who played an odd number of games here, and then plus others who played.
Yes. Oh, I like this. This was an idea I was having too. Okay. Okay. See where you're going. Okay.
Okay, an even number of games. Okay. Now, suppose by way of contradiction, as you've just suggested, that the red piece here, the red people, let's call them reds and blues, right? The red people are the ones who played an odd number of games, and the blue ones are the ones who played the even number of games. Suppose those people who played an odd number of games, that number itself is odd. So suppose, by way of contradiction, we have an odd number here in this set, number of people here, right? Does it make sense? So let's make sure that we distinguish. Let's make sure so these are all those people who have played an odd number of games, and these are all those people who have played an even number of games. Now, suppose the number of those people who have played an odd number of games is odd. So I have like 5 people, let's say here, like A, B, C, D, and E, and each played an odd number of people. Like this guy played 3, this guy played 31, this guy played 11, this guy played 5, and this guy played 1. So each one of these odd number of them, I have 5 of them, and each one played an odd number of games. The total sum must be odd. This must be odd, right?
Yes. Total number of games they played must be odd because you're combining only odd numbers.
The total number, okay, so total number of games, number of games. Okay, let's consider twice the number of games. Because when I add those numbers up, when I add those with the blue ones here in a second, this would be twice the total number of games is going to be exactly that sum. Twice the total number of games is going to equal twice the total number of games is going to equal this odd number here, the gray odd number, plus the blue number, which is going to be, now notice that no matter how many people I have here, those others, it can be an even number or an odd number, that doesn't matter. Because they played an even number of games, the total games
always be even.
Total games, number of games is even. Games is even. Right? The total, I should say, the total sum of those guys is even. Okay, so the total sum here, sum is even. Agreed? I have some number of people, and each played an even number of games. Okay, so their total sum, this is an even number, This is an odd number. So notice that what we get is that some even number, which is twice the total number of games played, is some odd number plus some even number, which is impossible. What I'm summing up here is I'm summing up all the degrees, the number of games each person played.
Yeah.
This guy played 3 games, this guy 31, this guy 11, and so on. So if the number of games that these guys played, the number of games these guys reported that they played, in sum, their total number of reports is going to be twice the number of actual games played, actual tennis games played, which has to be even. On the other hand, you cannot get an odd and an even number sum up to an even number. So therefore, it's impossible for an odd number of people to play an odd number of games. Does that make sense to everybody? See, that's a proof. It's a proof by contradiction. Here's a real quick before we leave. So you're given some graph G, right? And it has 10 vertices. Each has degree 3. How many edges does it have? So help me out with that. So I want to know how many edges I have. if all I know that I have 10 vertices, the number of vertices is 10, and each vertex has degree 3. So somebody help me out.
Is it 15 number of edges?
Yes, that's correct. So why is that? Can you explain to everyone?
You just do 10 times 3, and that's the number of the total number of degrees, and they just divide by 2.
Yeah, it's you have 10 vertices, so each has degree 3. So that has to be twice the number of edges. Call it m. So m has to be half of 30, because twice that m is 30. So m has to be 15. That's it. 15 edges in that graph.